for the schematic diagram, you can label your parameters with this particular symbol. You can label the feed stream as F. You can label the distillate stream as D, and you can also label the bottom stream as B. So since you are looking for the binary components, binary mixtures, you only have A components and B components. Therefore, when you have two components, the mole fraction of component A will be labeled as XFA in the feed stream, XDA for the distillate stream, and XBA for the bottom stream. So the X here represent the mole fraction of component A in the feed stream, mole fraction of component A at the distillate stream, and mole fraction of component A at the bottom stream. The reflux stream is labeled as Ln. From this schematic diagram that you have labeled, you can divide the section of the column into three sections. The one which is above the feed inlet is called the enriching section. The one that is below the feed stream is called stripping section. For the given sections that you have in the column, you should have a different operating line for each section. So the operating line for the above section, above the feed stream, which is called enriching section, you're going to get enriching operating line. Okay. For the below section, below the feed stream section, you're going to use stripping operating line. So these are the symbol. But for the feed stream, you're going to have Q operating line. Okay, because this depends on the feed condition that you have, whether your feed is totally in vapor form or totally in liquid form, or maybe in a mixture of liquid and gas form. Now, let's discuss on the equations for the enriching section. Okay, first of all, you need to have an assumption or two assumptions where you need to assume constant molar overflow in the column. Okay, so you're going to use mathematical graphical method to determine the number of theoretical trays needed for the given separation of a binary mixture of component A and B. Okay, so based on the equations for the enriching section, so you're going to have overall mass balance which is F is equal to D plus B. F is the mass for the feed, D is the mass flow rates for the distillate, and B is the mass flow rate for the bottom. Okay, so you need to use this particular equation for the overall mass balance of your distillation column. And then you need to have mass balance on component A, where you have to multiply the mole fraction of component A for the relevant feed stream. So you have Fx Fa equal to Dx DA plus Bx Ba. Since you're dealing with enriching section, so you're going to have enriching operating line. So the symbol that we're going to use is EOL. Okay, So what is the equation of enriching operating line? In this enriching operating line, you need to deal with the reflux ratio. The symbol for the reflux ratio is R. And the formula for reflux ratio is given by flow rates of reflux divided by the flow rate of your distillate. So this is your distillate stream and this is your reflux stream. Okay, so since the name is reflux ratio, the value that you get for reflux ratio can be a number. Okay, it's just a number without any unit. So these are the equation for the enriching operating line. So you have y is equal to r over r plus 1 multiplied by xn plus xdA over r plus 1. Please remember, you need to solve for your r by substituting the flow rates of your reflux divided by the flow rates of your distillate.